Welcome back to another video. So we will be solving this A-level physics paper, May-June 2016, paper 4-1. Question number 1. By reference to the definition of gravitational potential, explain why gravitational potential is a negative quantity. So firstly, you need to know that gravitational potential is 0 at infinity. So let's write down that first. And if we look at this diagram, for example, this is an object which is at infinity, and this is a planet which is exerting a gravitational force on this object. Since we also know that gravitational force is an attractive force, so this object will be attracted to this planet, right? So if it is attracted to the planet, work is done. Hence, if the gravitational potential is 0 at infinity, so coming down it will decrease, and lesser than 0 are the negative values, so it will become a negative quantity. So another point that is important to note here is that since gravitational work is done by an object moving from infinity. Or you can say as it moves from infinity. So gravitational moving on to part B. Two stars A and B have their surfaces separated by a distance of this, as illustrated in figure 1.1. Point P lies on the line joining the centers of the two stars. The distance x of point P from the surface of star A may be varied. Okay. The variation with distance x of the gravitational potential at point P is shown in figure 1.2. So this is figure 1.2 and this is gravitational potential. This is the distance from star A. Okay. A rock of mass 180 kg moves along the line joining the centers of the two stars from star A towards star B. Use data from figure 1.2 to calculate the change in kinetic energy of the rock when it moves from point where x is equal to 0.1 10 to the power 12 to the point where x is 1.2 10 to the power 12 meters. State whether this change is an increase or a decrease. Okay. So let's say that let's state some relationship first. That change in kinetic energy will be equal to change in gravitational potential energy. I'm just writing it as GPE, right? Since we know that there is a relationship between GPE and gravitational potential, and what is that relationship? GPE, or gravitational potential energy, is equals to gravitational potential into mass. Now, how did we come across this relationship? You can see that if you write down the formulas of GPE, which would be Gm over R, and gravitational potential, which is Gm over R. So you see that in order to convert gravitational potential into gravitational potential energy, you are multiplying mass. You're multiplying this mass here with gravitational potential's formula to get GPE, right? So that's how the relationship has been produced. So now, using this relationship, we can say that at x is equal to 0.1 into 10 to the power 12, it is somewhere over here. Oh my god. Here, right? So this is 0.1 into 10 to the power 12. And let's read off the value of gravitational potential, which is minus 10 into 10 to the power 8. So let's write that down. At x is equals to 0.10 to the power 12 meters, gravitational potential is minus 10 into 10 to the power 8. You do write the units. I'm not writing them right now. And then at x is equals to 1.2 into 10 to the power 12 meters, gravitational potential is here, and then it's minus 14 10 to the power 8. So Now, according to this relationship, we can say that change in GPE could be found out by change in gravitational potential into mass. We have mass here of the rock, 180, and we can find out the change using these. Okay, so change in GPE is equals to 14 minus 10 into 10 to the power 8 to find out the change into 180 kg. And our answer of change in kinetic energy, remember that we found out GPE, change in GPE, and that is equal to change in kinetic energy, and that is 7.2 into 10 to the power 10 joules. That's our answer. Now to find out if it is an increase or a decrease, so let's go back to the graph. If you look at these gravitational potentials at these points again, at 0.1 into 10 to the power 12 meters, the gravitational potential was minus 10, and at this point it was minus 14. So what do you see? There has been a decrease in gravitational potential, and since there has been a decrease in gravitational potential, it means that there has been decrease in gravitational potential energy as well. And if there is a decrease in gravitational potential energy, it means that energy is being converted to kinetic energy. Or you can say that decrease in gravitational potential energy is equals to increase in kinetic energy. So let me just write it down here. Kinetic energy. So the change in kinetic energy is an increase. That's it for this part. At part 2, at a point where x is this, the speed of the rock is v. Determine the minimum speed v such that the rock reaches the point where x is equal to 1.2, 10 to the power 12. Let's look at the graph again. If we say that from this point, to this point, the rock is moving away from star A, and we say that the GPE is increasing. Why? Because it is going from minus 10 to minus 4. This is gravitational potential, and gravitational potential, according to the relationship with GPE, is directly proportional actually. So if it is increasing, the GPE would increase. So GPE is increasing, kinetic energy would decrease. So we can say that we can use this change of GPE to find out the speed at here, because kinetic energy is very low here. It is the lowest here. We need minimum speed, so we can find out the change in GPE and use it to put in the formula of kinetic energy and find out the minimum speed. So here it's minus 10, and at this point it's about 4.4 something. It's 4.4. Yes, it's 4.4. So 10 minus 4.4 to the power 8 into 180. This is our GPE, change in GPE, and that is equal to change in kinetic energy. So just and our answer would be 3.3 into 10 to the power 4 meter per second. Question 2. An ideal gas is assumed to consist of atoms or molecules that behave as hard, identical spheres that are in continuous motion and undergo elastic collisions. State 2 further assumptions of kinetic theory of gases. Remember that 2 has been given to us. You do not need to repeat them or you won't get the mark. There are many assumptions. You can write any 2 of them. You can write no interforces between except during collisions. Another thing you can write is maybe random motion of molecules or large number of molecules, or you can even say that total volume of molecules is negligible compared to the volume of containing vessel. helium may be assumed to be an ideal gas, show that the mass of one atom of helium is this. Okay, so we know that the unified atomic mass unit is 1.66 into 10 to the power minus 27 kg. And since we have 4 in helium, so you need to multiply this by 4. And then you have to also multiply it by 1000 because it is in kg and you need to convert it into grams. So and the answer we would get would be 6.6 10 to the power minus 24 grams. The mean kinetic energy of an atom of an ideal gas of an atom is given by the expression. Calculate the root mean square speed of a helium atom at a temperature of this. So since this formula is for mean kinetic energy, and we know that another formula for kinetic energy is half mv square, it would become half m mean square speed. Okay, so let's now half. We will take mass of one atom, which we found out here, but remember that this is in grams. We need to convert it to kilograms. So it would be 6.6 into 10 to the power minus 24 divided by 1000 into the mean square speed is equals to 3/2. Boltzmann constant you can see from the data that has been given before the paper. It is 1.38 into 10 to the power minus 23. And remember to take temperature in Kelvin. 27 plus 2, 73. And the answer that we will get would be mean square speed and not root mean square speed. So you need to take an under root for the answer. 1.88 into 10 to the power 6. Now the unit for it would be simply meter per second squared, both of them squared, so they would become meter square per second square. Okay, so that is the mean mean square speed, and then for root mean square speed you take the under root of 1.88 into 10 to the power 6, and that is 1.4 into 10 to the power 3. Number 3, state by reference to displacement what is meant by simple harmonic motion. So simple harmonic motion is simply acceleration proportional to displacement from a fixed point and acceleration and displacement are in opposite directions. Part B, a mass is undergoing oscillations in a vertical plane. The variation with displacement x of the acceleration of A of the mass is shown in figure 3.1. Alright. State 2 reasons why the motion of the mass is not simple harmonic. Okay, so the motion to be simple harmonic, the graph should show a straight line, and it should also show that the displacement in each direction is the same. But here you can see here the displacement is somewhere here, and then it's this, so they're not equal. So you can say that maximum displacements are different, or maximum displacements are not same. And the second point was that the line or the graph should not be curved. Part C, a block of wood is floating in a liquid as shown in figure 3.2. The block is displaced vertically and then released. The variation with time t of the displacement y of the block from its equilibrium position is shown in figure 3.3. Alright, use data from figure 3.3 to determine the angular frequency omega of the oscillations. This is very simple. We know that the formula of angular frequency would be 2 pi over time period. We can find out the time period through this graph, and it is the time taken for one oscillation. and it is this 0.8, right? So 2 pi over 0.8, okay, and that's 7.9 radian per second. The maximum vertical acceleration of the block. Okay, so for acceleration, the formula for simple harmonic motion is omega square x, where x is the displacement, and since we need maximum vertical acceleration, we need the maximum displacement. So from the graph, the maximum displacement is in this direction, so it's 1.5 and centimeters. So omega we found out first, 7.9 square into the displacement is in centimeters, so you need to convert it in meters, so that would be 1.5 into 10 to the power minus 2, and our answer would be the block has mass 120 gram. The oscillations of the block are damped. Calculate the loss in energy of the oscillations of the block during the first 3 complete periods of its oscillations. We have this formula for kinetic energy. So the change in kinetic energy could be found out, which would be equal to the loss of energy. So the change could be found out by half m omega square x naught square, which is the maximum displacement, minus x square, which is the displacement at the point you are finding out the kinetic energy at. So the maximum displacement was 1.5 into 10 to the power minus 2, and we need to find out after complete 3 cycles. So that would be 1, 2, and 3 right here. And this is 0.9, right? 0.9 into 10 to the power minus 2. So we're going to find out at here what is the change of energy. So half into mass is given as 120 divided by 1000 for kilogram, into omega square, which was 7.9 square, into x naught square, 1.5 into 10 to the power minus 2 square, minus 9, 0.9. Zero 0.9 into 10 to the power minus 2 square. This would give us an answer of 5.3 into 10 to the power minus 4 joules. Question number 4. State what is meant by the specific acoustic impedance of a medium. So the acoustic impedance of a medium is defined as the product of the speed of ultrasound in the medium and the density of the medium. Alright, the intensity reflection coefficient is given by the expression. Okay, explain the meanings of the symbols in this expression. If you remember that this is basically equal to IR over I naught. So alpha here would be equal to the ratio of reflected intensity and incident, I naught is incident intensity. Okay, remember that Z2 and Z1 are acoustic impedances of media on each side of the boundary. It's better that you memorize these. Part B, a parallel beam of ultrasound has intensity I naught as it enters a muscle. Okay, the beam passes through a thickness of 3.4 centimeter of muscle before being incident on the boundary with a bone. This is shown in figure 4.1. The intensity of the ultrasound beam as it passes into the bone is IT, or you can say I density transmitted. Some data for muscle and bone are given in 4.2. Calculate the ratio of IT over I naught. Look, so firstly, as the ultrasound beam moves through the muscle, right, its intensity decreases as it is absorbed by the muscle, right? So the intensity of the ultrasound transmitted in the muscle is obtained by, let me write it down here, So if I tell you through the diagram, obviously I naught is the intensity that is going in the muscle, and IM is the reflected intensity of the ultrasound that did not enter the muscle. Okay, so and this mu is linear absorption coefficient. So I'll say that IM over I naught is, for muscle it's 23, so 23 into the thickness of the muscle was 3.4 centimeters. We have to convert it in meter. Alright, so this IM over I naught is the fraction of the intensity of the incident intensity that has been transmitted in the muscle. Okay, so firstly we did this. Now what we can find out is actually this alpha that we saw here, this intensity reflection coefficient. So if you look at the diagram, what is coming at this boundary is IM over I naught, right? Because this is the fraction of the intensity that was transmitted on the muscle. So this is coming here. Now we need to find out the intensity reflection coefficient, because some of the fraction of this IM over I naught has been transmitted into the bone and some has been reflected at the boundary. So if we find out the alpha, which is the reflection or intensity reflection coefficient, we can find out what is this, what has been reflected, and using that we can find out what has been transmitted, and that would be equal to this, right? So if I write that down, some will be transmitted and some will be reflected. Using the values given for both of them, our alpha is coming out to be 0.33. Now comes the important part. Do not make the mistake of taking that 0.33 directly. Remember that 0.33 is actually this. It's not IT, it's the reflected fraction of this. So it's 0.33 here. In order to obtain this, you need to subtract this from 1. So to find out the transmitted intensity, you need to subtract the reflected intensity from 1. And that is the alpha that we found out, which is 0.33, 0.67. Now what is this 0.67? If you remember that, so this is actually the fraction transmitted, which is IT over IM. This IT over IM is the fraction of the beam that has been transmitted in the muscle. It is not the fraction of the incident intensity I naught. Therefore, we need to take the fraction of the intensity that has been transmitted. That is IM over I naught. So now, what we were asked in the question was this. and IT over I naught would be equal to IM over I naught into IT over IM, right? So this could be cancelled and you could find out that. So we know IM over I naught is this. So e to the power minus 23 into 3.4 into IT over IM is this 0.67, and that would give us the answer of 0.31. Question number 5. The variation with time t of the voltage level. Okay, so this question is actually not the part of A-level physics syllabus now, so we're going to skip this. Question number 6. A solid matter sphere of radius this is isolated in space. The sphere is positively charged so that the electric potential at its surface is this. The electric field strength at the surface is this. On the axis of figure 6.1, show the variation of electric potential with distance x from the center of the sphere for values of x from 0 to 3r. So the formula for electric potential is kq over x. So we know that electric potential is inversely proportional to x. We also know that the electric potential inside a metal sphere is constant. So the radius is r. So inside would be from 0 to r, right, the distance. So it would be constant at Vs, right, till r. So let's till here is the r. And if we try to, what will happen to the potential if the distance is 1 over 2 r? So it is being halved, right? The initial potential is being halved. So at 2r, it would be the half of this. So that would be 0.5 Vs. It would be somewhere over here. And then if we take 1 over 3r, that's 1 over 3 of the original value. So that would be 0.33. You can say that it would be over here somewhere, right? And just draw the curve. That's it. Part B. On the axis of figure 6.2, show the variation of electric field strength with distance x from the center of the sphere for values these. Okay, so let me write down here. Inside a metal sphere, electric potential is constant. Electric field strength is 0. Remember these 2 points. It would be easier to draw these graphs. So from 0 to r, electric field strength would be 0. Right, and then let's write down the formula for electric field strength. It would be k q over x square. So electric field strength is proportional to 1 over x square. So at 2r, it would be. Also, we saw that it was written that electric field strength at the surface is Es. So at surface, which would be on r, it would be here, right? 1 Es, 1 Es, and we can draw this line. And then for 2r, it would become 1 over 4, right? Because 2 is squared. So 1 over 4 of the original value of Es would be 0.25. So at 2r, it would be 0.25. Somewhere over here. And for 1 over 3, which would become 1 over 9, that would be 0.11. So at 3r, it's 0.11. So that would be somewhere here. Just draw the curve now. That's it. Question number 7. A student sets up the circuit shown in figure 7.1 to measure the charge on a capacitor for different values of potential difference across the capacitor. Okay. The variation with potential difference V of the charge Q stored on the capacitor is shown in figure 7.2. State and explain how figure 7.2 indicates that there is a systematic error in the readings of one of the meters. Remember that whenever you see a line that is not passing through the origin, there is a systematic error in it. So and why should it pass through the origin? Because charge should be proportional to the potential difference. Use figure 7.2 to determine the capacitance of the capacitor C. So for this part, you need to draw the line of best fit on the graph. You need to draw this on through these points, the line of best fit. Remember that there should be equal number of points on either side of the line. And then what you do is you take out 2 points on that line to find out the gradient. So I've already done that, and the 2 points that I have taken are 0.60 and the other one is 5.4, 13.5 into 10 to the power minus 3. Make sure you're not forgetting this 10 to the power minus 3. So now capacitance would be y2 minus y1, x2 minus x1, and we get 0.002815. Now remember that we have to give answer microfarads. So for that, it would become, you have to multiply by 10 to the power 6. So it would become 1, 2, 3, 4, 5, 6, 2, 8, 1, 2. And that would be to 2800. Use your answer in B to determine the additional energy stored in the capacitor C when the potential difference across it is increased from 6 to 9 volts.